Hi everybody and welcome back. This is example 11-7 and you may recall that we changed some of the numbers around. But either way, this deals with the rotation of the Earth. All right. It's kind of interesting that that it is true that regardless, or that if at sea level, if you are at the equator versus if you are at the poles, you're actually going to weigh less. And it's because of this. So let's say right here is the North Pole and there's a South Pole down there. All right, and the Earth is, here's the equator. All right, and the Earth is rotating that way. If you stand at the North Pole, you are on top of that rotating axis, which means you aren't really going anywhere. You're not traveling anywhere. You're just spinning around in place. All right, but if you're standing at the equator, you are zooming around the widest part of the Earth very quickly, once every 24 hours. All right, you're making a lot of time. So what actually happens is that you're kind of the Earth is trying to fling you off at the equator. The Earth isn't really trying to fling you off right here at the poles because you're not really traveling anywhere, but you are partially being flung off if you stand at the equator, or also anywhere in between the equator or the poles, but most so at the equator because that's where you're moving the fastest. Okay, so that's the whole premise right here. It's true that as you go up in altitude, your weight increases or decreases. By the way, I should point out, but that's not what we're talking about here. We're talking about at sea level. All right, so what is the difference in their weights? All right, one thing that should be pointed out, it's the equatorial radius, that is from the center to the edge. We'll call it the radius of the Earth right there. That is 6,378.1 kilometers, all right, which we should probably convert to meters, right? So we'll move that decimal point over 3 more spaces to the right. 6,378,100 meters. That's our radius. That'll be important. One other thing we should probably know, we are going to be talking about centripetal acceleration right here. And centripetal acceleration is v squared over r. All right, we don't really know the velocity. We do know the radius, but we don't know the velocity. Centripetal acceleration is also 4 pi squared r over the time period squared. All right, we have the r. Do we have the time period? Well, yeah, we do. Remember, we're talking about the Earth rotating, right? So how long does it take the Earth to rotate one time? It takes the time is 24 hours. Now, we needed that in the seconds, so if we convert hours to seconds, 1 hour, that should be in H, 1 hour to 3,600 seconds. That should give us our rotation time, or time period, in seconds. So 24 times 3,600, 86,400 seconds. All right, that's the time period for a given day. So those will come in handy. All right, we've got our radius and we have our period. Let's go about solving for what the weights of these two people are. Okay, first of all, at the North Pole. Let's do the North Pole first. Well, the person is standing there, all right? So they're not sinking into the ground. They're not rising up off the Earth's surface. So that means the forces on them must be balanced. mg is directed downwards, and so that weight force, or you could call it the normal force, the supporting force, right, is going to be directed upwards, right there. All right? So that means the normal force, if the net force on the person is 0, and the net force equals the normal force minus mg. In fact, I should turn that around, because aren't we calling towards the center of a circle? Aren't we calling that positive? So I should probably say mg minus the normal, or the weight force right there. Either way, it doesn't really matter. Because if the difference between them is 0, then we can say, all right, well, the normal force of that person at the pole, I should say, and P equals mg. All right, and I should be able to do that in my head. We've got a 100 kilogram person. We know what G is. G is 9.81. So 9.81 times 100, what's that going to be? That's going to be 981 newtons that the person will weigh at the North Pole. Okay? Great. But at the equator, there's something different going on. Since they are moving around rapidly in this circle, there's another force, or there's another acceleration acting on that person. Let me shrink this down a little bit so we have some more space right here. And I'll put that up there. All right, so at the equator, so part B, at equator, let's sum up the forces once again. All right, at the poles there's no centripetal acceleration, but at the equator there is. The net force at the equator equals, well, I won't call it E, I'll just call it net centripetal force, I should say, is a mass times the centripetal acceleration. We can always say that's true, just like we always said it was true when we dealt with Newton's second law. In fact, that is a variety of Newton's second law. All right, that's true. What else is true at the equator? Well, what else is true is the fact that we have some component forces acting against each other. I'll do these in green. Okay. Remember, our friend at the equator right here has a weight force directed down towards the center. That's mg. And there's a normal force, or a supporting force, or the actual weight of the person if they were standing on a scale, that is directed upwards. All right? So, we can say that the net force, net centripetal force at the equator, is going to be mg minus the normal force. All right, now the reason I did mg minus the normal force is, again, towards the center of the circle is positive, towards the outside is negative. So this is the positive direction, that's the negative direction. All right, so gravity is pulling the person down. All right, the normal force is the supporting force that a scale would read. But the difference is that we have this centripetal acceleration going on. Look at what we have here. We've got two statements for net force, which means we can set them equal to each other. mg minus the normal, or the supporting or weight force, equals mass times centripetal acceleration. All right, now remember, we're solving for that normal force, or that supporting force that a scale would read. So let's just turn around and solve it for that. Normal force equals, let's see, mg minus m times centripetal acceleration. All right? Good enough, but we don't know our centripetal acceleration quite just yet. We would probably do well, mg minus mass times what? We would probably do well to write that as a statement. All right, well, what's the equation for centripetal acceleration that we talked about using before? We can't use v squared over r because we don't know the velocity. But we do know 4 pi squared. We know r, and we know the time period. That's why we took the time to actually figure out what that was. We've got the radius here, and we have the time period, so we should be able to say that centripetal acceleration is 4 pi squared r over t squared. All right? So now we should be able to solve for the normal force at the equator, the supporting force, the force that a scale would read. You know what? I'm going to do one more thing. I'm going to factor out these m's right here and put it out front. And so mass out front times the quantity g minus 4 pi squared r over t squared. All right. Now we can plug in our knowns because this is our final general equation where we can solve for the normal force. So the mass of the person, which is 100 kilograms, times g, 9.81 meters per second squared, minus the quantity 4 pi, that's a known, right? That's a constant. Sorry, 4 pi squared, times the radius r. Oh, here's that really, really big number. Here's our radius right here, 6,378,100 meters. Okay, all over the time period squared. That's 86,400 seconds. That's squared. All right, so let's see. I close that up, close that up. I'll close that up, and I think we're all set. Does that look right? Mass, gravity, 4 pi squared r over time squared. Great. Let's crunch some numbers and see what we get. And I got a feeling that we're going to have less of a weight or a normal force at the equator than we do at the poles. All right, and after a couple of seconds of punching into my calculator, I get 977. Well, I'm going to round that up. I'm going to round it up to 978 newtons. Okay? That is our weight force, or I shouldn't say our weight force, I should say our apparent weight at the equator. The weight force is really mg, but it's the apparent weight, what the person weighs at the equator versus at the poles. Here is the weight at the poles, 981 newtons. At the equator, they weigh about 3 newtons less. Why is that? Well, because the Earth is rotating, and at the equator, it's trying to fling us off. And the only thing keeping us stuck to the Earth is gravity. So the flinging off force is kind of cutting into the gravity force a little bit, making you actually weigh slightly less at the equator. So if you ever want to be a long jumper or a high jumper or just jump for fun, go to the equator. You'll probably have a better chance of getting your record height. So question C, does the weight your scale measures increase or decrease as your latitude increases? So, all right, so at the equator is 0 latitude, and this way we've got higher latitude, and this way is considered higher latitude as well. The equator is considered 0 latitude, so it's lowest. So it's basically saying as you move towards the equator, what happens to your weight? And so the answer to C is, as latitude increases, weight, or I should say apparent weight, does too. All right, we solved for apparent weight using normal force, because normal force is kind of your apparent weight. But we have used this notation before as well. As you move towards the equator, you actually get heavier, or you feel heavier, because the Earth isn't flinging you off as much as it is at the equator right there. So there we go. That's example 11-7, and I hope that makes sense to you. If it doesn't, make sure you come see me. But in the meantime, thank you for watching, and I'll see you on the next one.